So we're going to continue talking about optimal social insurance today. So if you remember where we left off at the end of the last lecture, it was this consumption-based formula for optimal unemployment insurance where you had to estimate two parameters in addition to the elasticity of the unemployment rate with respect to the unemployment benefit level, which were risk aversion and the consumption smoothing benefit of the insurance policy. And as we talked about for various reasons in the last lecture, not only is delta C over C hard to identify empirically because of poor consumption data, basically, but also the risk aversion parameter is highly variable across contexts for both behavioral and neoclassical reasons, and so it's hard to pin down exactly what those two parameters are. So one way to think about what more recent work has done is to seek alternative ways of calculating optimal benefits that do not require the estimation of these two parameters. I think more generally, this is kind of an illustration of the type of approach that people are taking in the literature where you think about what data you have, what you're able to estimate credibly, and then find a representation of the formula for optimal policy in terms of those parameters rather than just starting ex ante based on having no idea what you'd be able to estimate in the data. And so the way to think about this is all of these formulas are just different ways to calculate the optimal benefit in the same set of models, right? So if you were estimating all of these parameters correctly, in principle, all three different formulas that we're talking about should give you the same answer for what the optimal benefit level is. Now, to the extent they don't, that means that some of the estimates are inconsistent with the others, or something is wrong about the assumptions made to derive these formulas and so forth. But the point is you should just think of these as different representations of the same underlying calculation of optimal benefits within this class of models. So today we're going to talk about two approaches. The first is this moral hazard versus liquidity approach, which is basically like an income versus substitution effects decomposition. And then the second is using data on reservation wages, which is the paper by Scheimer and Werning in the QJE, and this other papers in the JP. So let's start with the moral hazard versus liquidity. So I'm going to set this up a little bit differently than the basic Bailey model, partly because I want you to see what a standard job search model looks like, which is used very widely in this literature. And so I think it's useful to be familiar with the notation and then the basic dynamic programming tools that are used to characterize the solution to these models. But the formula that we derive would also apply in the Bailey type of setup. Okay, so we're going to spend a little bit of time setting up this job search model, and then we'll talk about optimal policy again. So consider an environment where it's a discrete time dynamic search model. So individuals live for T periods, a finite horizon. For simplicity, we normalize the interest rate and the discount rate to 0 and assume that the individual loses his job starting in period T equals 0. So you're starting with a guy who's unemployed, and then he's looking for a job over time. That's what a job search model is. And we're going to study the dynamics of how he's going to find a job and how that depends upon the policies. This assumption that the guy starts out unemployed, the only sense in which it's important is that you're not allowing for the policies to distort behavior prior to the point of job loss. So like, for instance, the amount he's working on his previous job or his savings behavior and so forth. In the basic version we're going to talk about here, that stuff is all fixed. That's the way to think about it. You can show that the sufficient statistic formula that you derive ends up still going through even if some of those choices are endogenous, and I'll come back to that. So we let U of CT denote flow utility over consumption in period T. And then the way to think about budget constraints in these dynamic models, I think the easiest way to think about it is as a flow budget constraint. So your assets in period T plus 1 equal your assets in period T plus the amount that you save, which is your income minus your consumption, right? And then there's what in an infinite horizon model would be called a transversality condition, or a there's something that closes the model which says you cannot just simply run up debt, right, and die in debt. And so in particular, the way we're going to impose that here is we're going to say period by period, actually, we're going to allow for a borrowing constraint. So AT has to be greater than or equal to some level L. So if L is 0, for instance, that means you cannot borrow. You always have to maintain positive assets. Or you could have L as some negative number, right? But we're basically incorporating the fact that agents face borrowing constraints, or we're allowing for that, which, as we know, is important in these dynamic models. Otherwise, people are just going to be able to smooth consumption perfectly, more or less, by borrowing. And you're not going to find much of a role for insurance. So we want to be able to accommodate that. And one of the things I want to stress here is we don't really have a good idea empirically of what L is, right? For some people, it might be 0, like you literally can't borrow. For other people, they might have some credit card limit. Getting a handle on what L is very difficult. And that's one of the structural parameters of this model, which it turns out we will not need to estimate in order to say something about policy. So there are 3 assumptions that are important in the basic version I'm going to show you here. The first I already mentioned, which is assets prior to job loss are exogenous. The second is that I abstract from heterogeneity. So heterogeneity, so what I mean by that is, for instance, some agents might have different utility functions than others, or different job finding probabilities and so forth. That in all of these models, generally heterogeneity doesn't make a difference as long as you average over people when you're calculating the sufficient statistics. Basically, it works out that what are you going to end up maximizing? It's going to be some weighted average of utilities across agents. And then you can show that instead of measuring the elasticity for the individual guy with respect to benefits, you measure the average elasticity across agents. And you can see that if you take some approximations, basically, that's going to work out properly. And then the third assumption is that we assume wages are fixed. So this is a pure search intensity model where the only way you control when you find a job is by how hard you search. So think of it as like how many doors you go knock on to find a job, or how many applications you send out, rather than selecting which job offers you accept, which would be a reservation wage model. Turns out, again, that the formula works in a reservation wage model as well. So the way to think about the formula that we're going to derive is that it works in all of the models that are used in the structural job search literature. One of the most famous papers in that literature is by Ken Wolpin, where he calculates optimal unemployment benefits after estimating a structural job search model. And the point is, the formula that we derive here would apply in that model without having to estimate all those parameters. All right, so here's how the model works. If you're unemployed in period T, the first thing you do is choose how hard you search. You choose your search intensity ST. And as in the previous model we were thinking about, I'm just going to assume as a normalization that search intensity translates linearly and directly into the probability of finding a job. So you find a job that begins immediately in period T itself with probability ST. If you find a job, you consume some amount CET. And I'm going to assume this is a standard simplification in these dynamic models. We assume that jobs are permanent once found. So we don't allow for secondary unemployment risk once you find a job. That ends up, the reason that's really convenient analytically is that you can see it sort of cuts off one set of branches of the tree. Once you find a job, the problem becomes totally simple. There's no more uncertainty. And we can very easily solve that part of the tree. So we assume jobs are permanent and pay a wage of some amount W sub T. We can allow the wage rates to vary across periods. That doesn't matter. Minus tau, the tax that's used to finance the unemployment benefit. OK, if you don't find a job, that's the more important case here. That's where the solution is going to be more complicated. Then you receive an unemployment benefit B sub T, which in principle we can allow to vary across time. So it can be varying across the weeks of the unemployment spell. You consume some amount CUT, and then this is where the problem becomes, the dynamics are interesting. You enter period T plus 1 without a job, and then the problem repeats itself, okay? So if you think about, from the perspective of period T, you pick ST, right at the beginning. With probability ST, you go down this path here, where then you're in this absorbing state of employment. With probability 1 minus ST, you go down this branch of the tree, and then you choose a level of consumption, CUT, and then you enter period T plus 1, where you face the same problem again. Okay? But same problem in terms of its structure, but obviously it's not a stationary environment because you're going to be depleting your assets. So you're getting poorer as you go through this unemployment spell, and it might get harder to find jobs and so forth. And so your choice of ST plus 1 won't necessarily be the same as your choice of ST. Now, there's a cost of setting ST very high. I mean, what you'd like to do is maximize the probability you go down this branch, but there's a cost of search. And so we call that psi of ST a convex function, just like in the Bailey setup, right? Okay, so the way you solve, let me step back for a second. So what are we trying to do? We're trying to say, given a path of benefits and a tax system, how is the agent going to choose search intensity, and how is he going to choose consumption? So at an abstract level, solving that problem mathematically is like any other problem we've discussed solving this class. It's just optimizing over several variables, right? You're choosing consumption in each state, and then you're choosing search intensity, so that's 3 variables per period. And then, if you think about like a 50-period model, let's say 1 period per year of the agent's life, you've got 150 choice variables. And so just from like a mechanical point of view, you can see that if I give you an optimal path of benefits, I'm trying to maximize as the agent my expected lifetime utility, right? You can see how, like, imagine running a loop with a computer. For each combination of these 150 choices, I can figure out what my utility would be. And then I can find the utility maximizing set of choices. Okay, so optimizing over 150 variables like that is not feasible because it's too high dimensional of a space. So what is dynamic programming? It's basically a way to solve a model that has a recursive structure like this much more easily computationally. Okay? Okay, so the way I'm going to characterize the solution to this and derive formulas for the marginal welfare gain of changing benefits is by writing down a set of value functions, okay, which is the standard way to think about dynamic programming problems. So what's a value function? It's basically the expected utility an agent would have over his remaining life given the state variables that he enters that period with. So the state variables are, if I enter period T with a certain level of assets, I'm going to be able to achieve a different level of utility than if I entered with a lower level of assets, right? So the amount, there are going to be a certain set of variables that determine the maximal level of utility that I'll be able to attain in each period. And those are predetermined based on prior choices. So in this case, the only state variable that's relevant, the way this model is set up, is your level of assets. Nothing else ends up mattering for future utility. So in particular, like you can see, one thing that's been ruled out is that past search decisions have no bearing on the future utility that you can attain. So you might think of a model where, let's say, there are only X job applications that you can send out, and if you've sent out lots of applications in the past, you've had really high search intensity, then there are just not that many opportunities left, and so that reduces the utility that you can achieve going forward. It narrows the set of possibilities you have. So that type of issue is ruled out by assumption in this model, right? The only thing that matters when you enter period T is the amount of assets you have by the structure of the model. Okay, so think of VT of AT as basically being your indirect utility when you enter period T with assets of AT. And I'm going to use V to denote the value function for an agent who finds a job in period T. So the guy who chooses ST and gets lucky and is successful and finds a job. So what is the expected indirect utility that he'll attain over the remaining periods, given that he's found a job? So here there's no expectation to take because remember there's no uncertainty once you find a job, right? It's totally deterministic. And so this is the recursive representation. So the value function in period t can be written as the sum of two terms, one of which is the flow utility in that period, and the other of which is the utility that you get going forward, which is determined by the value function in the next period, right? So this is writing the indirect utility in period t recursively as a function of the indirect utility or the value function in period t plus 1. All right, so in this case, when you're employed, you only have one choice variable, which is in any given period, which is the amount you consume in that period. Or you can equivalently think of it as how much do you save for the next period, which is like choosing AT plus 1. What's the level of assets you enter period t plus 1 with? So the way you can write this is if you look at this term here, AT minus AT plus 1 plus W minus tau is consumption in period t. If you just work out the budget constraint, okay? It's like the amount that you're dissaving plus your income is your current consumption. And then VT, AT plus 1 is your utility in the next period, your present value of utility in the next period, depending upon the level of assets you chose. And you are going to choose the level of assets that maximizes the sum of those two terms. So does that make sense? That's the optimal choice. And then this is why you think of this as the indirect utility. It's the maximum level of utility you can attain when you make this choice optimally, subject to the borrowing constraint. Okay? So that's the value function when you're employed. Now, analogously, there's a value function for an agent who's unemployed and is unsuccessful in job search in period t. All right? And I'm going to call that u sub t of AT. And it has exactly the same structure where here what determines your flow utility and your consumption in period t is not the wage, it's the benefit, because you're getting the unemployment benefit instead of the wage minus the tax. And then you have another continuation utility term, which I'm going to call J. And JT denotes the value of entering the next period without a job. The expected value of entering the next period while unemployed. Okay, and again, that's going to be a function of your assets in period t plus 1. Okay, so this is totally symmetric to that, where JT plus 1, the difference between VT plus 1 and JT plus 1 is here you enter the next period and you know you have a job. In the other one, you enter the next period, and there's uncertainty because you might find a job and you might not find a job in the future. And so that generates this different value function, JT plus 1. Okay? So JT plus 1, AT plus 1 is the value of entering the next period unemployed. And lastly, the thing I'm going to do is specify what JT looks like. And that sort of closes the specification of the model. And so the way to think about that is the agent is choosing his level of search intensity in order to maximize his expected utility. Okay, so the agent is choosing ST in each period in order to maximize his expected utility, and hence JT of AT, the expected utility that he attains in period t, is given by the just the weighted average of the utilities in the two states, right? So if he finds a job with probability ST, he gets VT of AT. And if he doesn't find a job with probability 1 minus ST, he gets this value here. And then there's a cost of job search. And that's the expected value of showing up in period t with assets of AT and not having a job. That's the best you can do, right? If you choose your search intensity optimally, given the value functions. Okay, so this completely specifies the agent's choice. And then this is where I think this structure is useful. Turns out I'm not actually interested in characterizing the complete consumption path that solves this model. We're going to get everything just off of what the derivatives of this value function, JT, look like. That's what turns out to be central. Okay, so let's think about optimal search behavior. And the main idea of this paper is you actually don't need to know anything about consumption to say something about optimal policy. You can get it all completely off of search behavior, which we know is much easier to characterize empirically because we have good data on unemployment durations or other measures of sort of effort, like labor supply. All right, so the first thing we start from is a condition that we know has to hold at the optimal level of search, which is this first order condition for optimal search intensity. And that's just differentiating this expression here and setting the derivative equal to 0. And so you get this first order condition that psi prime of s has to equal v minus u. So what's the intuition for that? It's very straightforward. The left-hand side is the marginal cost of supplying one more unit of search effort, and the right-hand side is the benefit of supplying one more unit of search effort, where remember, search effort translates directly into the probability of finding a job. So if I increase search effort by 1 unit, I raise that probability by 1 unit. And what's the benefit of finding a job? It's getting the value v instead of the value u, right? If I find a job, I get this value. If I don't find the job, I get that value of u. And so that's the net gain from finding a job in the value function notation, right? So now everything that follows is going to be driven by the comparative statics of that first order condition. So first, let's think about an experiment where we look at the effect of a change in benefits on durations. So this is the Bruce Meyer kind of thing, or Camille Landé, the numerous papers that estimate the effect of changes in benefits on durations. We're very good at estimating this parameter. So what is that here? dst dbt is given by minus u prime of cut if you differentiate this, divided by psi prime prime of st. So where is that coming from? There are actually envelope conditions that are being exploited here. So there's no bt that enters directly in the value when you're employed. The level of unemployment benefits is irrelevant once you're employed, okay? If we don't think about the change in taxes. So forget about the government budget constraint for a moment, just a partial derivative with respect to benefits. What is the impact of a increase in benefits when you're unemployed? That's just given by the marginal utility of consumption in period t. So I'm differentiating with respect to b sub t, so benefits in a given period, like period 3 or something. What's the impact of raising benefits in period 3 by $1? It's just the marginal utility of consumption in that period. And why is that? That's again because of an envelope condition that you are going to re-optimize your search behavior and consumption behavior, savings and everything else when I change benefits, but none of those changes is going to have a first order impact on your value going forward. And so I only need to sort of look at the place where the b appears directly, and that's why I only get that marginal utility there, all right? And then the psi prime prime is just coming from differentiating the left-hand side and then dividing. Okay, so here's the key idea, basically, of the paper. So the benefit effect can be decomposed into 2 terms, and this is actually totally parallel to a Slutsky decomposition that we talked about in the beginning in the context of efficiency costs of commodity taxes. So I want you now to think about 2 different experiments. In the first experiment, I give everyone a $1 cash grant. So that's an increase in assets. I just give people more cash, okay? So how does that affect search intensity? Let's calculate that algebraically. Again, all of this is just coming from implicitly differentiating this first order condition, right? Okay, so when I give you $1 of cash, that affects your value function in both the state where you have a job and in the state where you don't have the job, because you get the money either way. It's just cash, right? And so what's the impact of that? Well, you get an extra u prime of CE in the employed state, and then there's a minus u prime of CU in the unemployed state that's coming from the u term. And then again, you have the psi prime prime in the denominator. So dsdA is given by this difference in marginal utilities divided by psi prime prime. So just mathematically, it's just the derivative of, that's just what that derivative is from the first order condition. Okay, and then we'll talk about the intuition in a second. Now consider a second experiment where I raise your wage for the job in period t and don't do anything else. So that increasing the wage only affects the value function when you're employed. If you don't have a job, the wage doesn't matter because you're not getting paid the wage. And so that ends up having a u prime of CE term here, okay, that's coming from differentiating the v. And there's no term coming from the u, and again, divide by the psi prime prime, and that gives you this derivative. So this derivative here has to be negative. How do we know that? Because if you're not perfectly insured, then the marginal utility of consumption is going to be higher when you're unemployed than when you're employed, because CU is lower than CE, okay, and U is concave. And we know this derivative has to be positive because the marginal utility is positive, and giving you an extra dollar is just going to give you more consumption when you're employed. So now you should be able to see a couple of things. Well, you can anticipate where I'm going to go with this, which is this gap in marginal utilities, remember, is exactly the thing we're trying to recover to get at optimal benefits, right? It tells you the value of transferring money from the high state to the low state. And you can see that if I divide these two expressions, I'm going to get exactly that gap in marginal utilities that we're trying to identify in the Bailey formula and in our prior analysis. So I'll come back to that, but that's sort of where we're headed. But so let's just talk about the intuition of what these derivatives capture. So you can write dst dbt, if you just look at these two expressions, as dst dat minus dst dwt. So in other words, you can decompose the effect of a benefit change on search intensity into two parts. One that I'm going to call a liquidity effect. It's kind of like an income effect in a static model. And the other is a price effect, or you can think of it as a moral hazard effect in this context. So what is the effect of raising your unemployment benefits by $1? It does two things. One, it gives you more cash on hand. It raises the amount of money you have, okay? And that may change the amount that you want to search, just because when you feel richer, you don't feel as pressed to get a job, and so you end up searching less hard or being more selective in the type of jobs that you take. So that's the liquidity effect. The other effect is the distortionary effect that we're really concerned about from a policy point of view, that when I raise your unemployment benefit, it's as if I have cut your wage by $1 because your net wage for finding a job has fallen. And that's the distortionary moral hazard effect, which is going to make unemployment benefits less desirable, all right? So that decomposition, makes sense intuitively. You can sort of think of an unemployment benefit increase as combining two things, providing a cash grant and distorting wages or putting in a tax. And it turns out that we can estimate both of these in the data, and the relative magnitude of liquidity and moral hazard effects is going to tell us something about optimal policy, all right? So one of the key ideas here is that liquidity and total benefit effects are going to be smaller for agents who can smooth consumption better. And you can see that algebraically here, that if I'm a person who has a lot of private insurance, then U prime of CE and U prime of CU are going to be really close, and the liquidity effect is going to be small, and the benefit effect is going to be really small. So let me just show you what that looks like in a simulation, which is of this job search model, which has been calibrated to match the data that I'm going to talk about. All right, so let me just show you in a simulation how this works, and why you can get very different effects of unemployment benefits because of these liquidity effects. So take two agents, one of whom, let's say, has a significant amount of assets, $13,000. I think I picked this because it's like the 75th percentile in the data that I look at. And then another guy who really doesn't have any money when he loses his job. He's at minus $1,000. Okay, so he's like hitting up against this borrowing constraint. And I'm plotting two things. So on the y-axis is the probability of finding a job in period 0, which you can think of as search intensity in period 0. how hard did you search, or empirically, the way we're going to observe that, what's the probability you found a job? And so the first thing you can see is that, and so then on the x-axis, I'm varying unemployment benefits, or I'm varying the size of a cash grant that I'm giving you. Technically, actually, the way you have to do it is not a cash grant. It has to be an annuity, where I give you a fixed dollar amount in each period. That's what makes it exactly identical to a benefit stream. But that's a technicality that's not that important. So we're varying cash grants and benefits. And the first thing you can see is that for the guy with very little cash on hand, this curve is very steep. So as you give him more benefits, he's starting to search much less hard. Or another way to look at it is when you cut benefits to a very low level, he starts to search really intensely to find a job. And why is that intuitively? If you have no other resources and you're not able to smooth consumption, you're desperate to find a job. And if I cut benefits, I'm going to find that you'll do anything possible, exert a tremendous amount of effort, and bear tremendous cost in order to find a job quickly. And that is entirely driven, as you can see by the red curve, which is the annuity part, it's entirely driven by this liquidity effect being really big. For the guy who has a lot of assets, the liquidity effect is essentially zero. It basically doesn't make a difference what the level of benefits are. And the reason that it doesn't make a difference how much cash he has. The reason that search intensity does vary with the level of benefits is purely due to the price effect rather than the liquidity effect. So you can see now that these are two very different scenarios where in this case, we might see really high impacts of unemployment benefits on unemployment durations, but that doesn't necessarily mean the unemployment benefit system is bad from a welfare or efficiency point of view. In fact, it's just that you are correcting this problem that this guy has no liquidity. You're relaxing this borrowing constraint. And so the provision of insurance by changing behavior can actually be beneficial. It's allowing him to make a choice that he would like to make but is not able to make because he's borrowing constrained, whereas the price effect is just a pure distortion. Okay, so let's now see how we can formalize that idea and get a formula for optimal UI. So this is the liquidity effect. This is the price effect. So we take the ratio of the two, which is the ratio of liquidity to moral hazard effects or income to price effects. And we end up getting this expression here, which is that familiar gap in marginal utilities that we saw in the previous analysis. And then I'm not going to rederive this in this context, but you can basically show that the Bailey formula for optimal benefits again holds in this model. Okay? So the optimal level of benefits is going to be characterized by this condition. And so then just plug this liquidity moral hazard ratio into this formula, and you end up getting a formula that depends solely on duration elasticities. So I can write the condition for optimal benefits purely in terms of the effect of changes in assets on search intensity and changes in benefits on search intensity. So notice in this formula at the bottom of the page where it's just rearranged in terms of elasticities, all of these parameters can be estimated using administrative data on unemployment durations. You don't need to know anything about risk aversion. You don't need to know anything about consumption. Okay, so let's talk for a minute about the intuition of this formula and why I think it can be applied in other contexts, which are probably more important, actually. And then we'll turn to the data. So we've gone through a lot of algebra and basically found it, almost may look like coincidental that it turns out that this ratio of income and substitution elasticities is the gap in marginal utilities you want to recover. But what is the economic intuition underlying that derivation? So one way to think about it is that the formula is basically a revealed preference approach to valuing insurance. So what I mean by that is we infer the value of the insurance policy to the agent by observing what he would do if the money was given as a cash grant that did not distort his incentives. So what I mean is the following. So when you give a person an insurance benefit like unemployment or health or whatever, it does two things. First, it sort of makes it affordable for them to make a choice that they wouldn't have been able to make without the insurance. So that's very obvious, like in the context of healthcare. when I have health insurance and I get sick, I'm able to afford a treatment that I would not otherwise have been able to afford. So one reason that I might use more healthcare when I have more health insurance is a liquidity effect. That is, I actually have more cash to be able to pay for a procedure that I needed to get when I have the insurance. A second reason that I might use more healthcare when I have more health insurance is because prices are distorted. So now I feel like it's really cheap to get more healthcare, or I feel like it's really cheap to stay out of work. And so so I inefficiently end up over-consuming healthcare or taking too long to find a job. So you can see that those two effects have different welfare consequences. And the way we figure out the size of the beneficial liquidity effect relative to the pernicious moral hazard effect is through this experiment of seeing what people would do if you just gave them cash. So think about a situation where instead of an unemployment benefit, I just give you, $5,000. Suppose the present value of your unemployment benefits is $5,000 over all the weeks. So instead, I give you $5,000 in cash when you lose your job. If I find that you use that money to still take an extra couple of weeks to find a job, then that must mean that the reason the unemployment benefit is making you take longer is because you were forced into making some suboptimal choice when you didn't have the unemployment benefit. But if I find that when you take the cash grant, and when you get the cash grant, you don't change your unemployment duration, but when I give you unemployment benefits, you do have a much longer duration, then that implies that it's the price effect that's making you take longer to find a job, and that's bad from an efficiency point of view. It suggests that it's a distortion rather than a benefit that's causing the behavioral response, okay? So more generally, and I think where this can be more powerful, is using this approach to value other types of insurance. So think about the context of health. So one of the problems in valuing health insurance is that you get into an endless debate about the benefits of providing more insurance, because you have to quantify how much it's worth to someone to not only have access to better health care, which might have impacts on measurable things like mortality, but also things that are very hard to measure like quality of life. But moreover, in the debates I've seen on this, some people will say, well, even if I don't see clear impacts on mortality, I think I want to have a more generous health insurance system because it makes the quality of care better. I have to wait less to find a doctor, or so forth and so on. Now, you can see that that outcome-based approach of trying to value insurance is complicated because you have to figure out the value of all those outcomes to the agent and weigh that against the government revenue leakage term. But here the idea is, the way you'd value the health insurance, to make an analogy, is give a person, when they're diagnosed with some condition, give them, the expected cost of the treatment. Like, so let's say it's $10,000 to get some procedure. I give you $10,000 in cash. If you choose to take that money and go buy a car, then I know that, if the insurance was making you get this procedure, that must be an inefficient choice, and so it's suboptimal. But if you choose to take that money and go get the same procedure, then it suggests that provision of insurance actually is desirable, right? And so you can see that if you compare these lump sum grants to the effects of the policy as they exist, you can learn about the benefits of the policy without having to take a stance on. Critical assumption here is that the agent is optimizing, right? That's the idea of the revealed preference approach. So let's take your example. If when you stay unemployed for a long time, it makes it harder to get a job, and you take that into account ex ante, then everything works because it's the same usual, you've optimized all the envelope conditions hold, et cetera, et cetera. You've sort of taken that effect into account when you make your choices. If you underweight that, which I think is actually plausible, then the formula is not right? Because you might mistakenly take the cash grant and say, oh, now I don't need to look for a job for a couple of weeks, but then that ends up really hurting you down the road. You didn't take that into account, and now we've miscalculated the value of the benefits. So critical that agents optimize. But I still think we've been searching for a while for like a health context where you can actually estimate these parameters, but haven't really been successful. I've talked to Amy Finkelstein for several years actually, trying to come up with a context, because we think that could be quite valuable. But I think that's an interesting open area for further research. Okay, so let's look at how this works empirically in the context of UI to be concrete. All right, so what I do in the empirical part of this paper is implement two strategies. The first, both of which are sort of geared to get at how important are these liquidity effects relative to the moral hazard effects. So why is unemployment insurance increasing the unemployment rate? Is it because it's giving people liquidity, or is it because it's distorting incentives? You can see why you want to distinguish between those. So the first approach, which goes back to the ideas of an old literature and consumption, is to divide agents into those who might be liquidity constrained versus unconstrained, and estimate the effect of benefits on durations using the usual changes in UI laws type of approach. So the idea of this is to look for heterogeneity in the impacts of UI benefits based on how liquidity constrained people are. And you saw from the simulation that I put up that if agents are liquidity constrained, then we expect benefits to have a larger impact because you have these liquidity effects. But if a guy has a lot of money in the bank, the liquidity effect basically becomes irrelevant. And if this whole theory is right that these liquidity effects are important, then we should see much smaller impacts of benefits on durations for that group. Now, that approach by itself doesn't tell you the relative magnitude of the liquidity and moral hazard effects, because we're just comparing different agents in the population, and unless we make a strong assumption about those agents having similar sized price effects, we can't figure out how big the liquidity effects are. So what you really want to do, ideally, is have a randomized experiment where you give some guys cash and don't give other guys cash, and compare their durations, and then compare that magnitude to an equivalent size benefit change. And that's what the second strategy tries to do. It looks at lump sum severance payments to estimate the size of the liquidity effect. Now, that variation is not great in the US. The data is not great in the US, so I'm going to talk about a subsequent paper which does this much better. So here's first just to get a sense, empirically of, why this might be important. So I use data from the SIP in this paper, Survey of Income and Program Participation, and take the set of people who lose their job in the panel and look at their liquid wealth, so excluding housing, liquid wealth prior to unemployment. And the first thing you can see is that people really don't have a lot of liquidity, okay? So these are the cut points. I've cut them into quartiles of liquid wealth. And so the bottom quartile, they have less than minus $1,000 when they lose their job, so that's 25% of people. Then 50% of people have less than $100, so that's why the median is like $100. And then these guys here have some money, at least they have positive balances, and then the top quartile actually has a decent amount of money saved when they lose their job. Okay, so these people up here perhaps are not that constrained, and then these guys appear to be quite constrained, and they are a substantial chunk of the population. So let's look at a bunch of survival curves, which basically tell you the story. So what this survival curve plots is the fraction of people who are unemployed after X weeks, right? And it does that for two groups. People who are living in state year pairs that have relatively generous UI benefits, so above the sample mean, and then people who are living in ungenerous state year pairs. So it's exploiting this cross-state time variation just as an initial visual, just pooling, above and below the median, right? And so the first thing you can see, right away, which is consistent with the prior results, is that people who live in live in environments where UI benefits are high have longer unemployment durations. That is, their probability of surviving in unemployment is higher at all points, right? That's why this survival curve is above this survival curve. So that figure is drawn for people in the lowest quartile of net wealth, the guys who have less than minus $1,000, the poorest guys. And so you see a pretty substantial effect for those guys, right? So now replicate this analysis for people in the second quartile of net wealth, the third quartile of net wealth, and the highest quartile of net wealth, And you can see that the effect of unemployment benefits on durations that Bruce and others had identified in the past is driven to a very large extent by people who have no money, who have no assets when they lose their job. So that makes it look like liquidity effects are actually quite important here. And it's not the traditional notion that people had in mind that people are thinking, oh, I effectively make less money when I go back to work, because that price effect should be there even for the guys who have substantial assets, right? They face the same distorted incentives. Okay, so that's the first clue, I think, that liquidity effects might actually be pretty important in this context. Then I'm going to skip this in the interest of time, but basically, the way you'd formalize this is this is the standard Cox hazard model where you have log UI benefits on the right-hand side, and you get an elasticity of a half, which I told you is typically what you get in this literature. And then here, what I do is interact this non-parametrically with the wealth quartiles. That's what I was showing you in the graphs. And you see this pattern that the elasticities are bigger at the bottom than the top. And then you can do an F-test for whether those coefficients are equal. Okay? And you see that they're not equal because the elasticities are actually bigger at the lower part of the distribution than the higher part of the distribution. But you can see, one of the weaknesses of the US data, and this is what got me interested in working with the other administrative data sets from other countries, is you're working with samples of like 4,000 observations here. So I think you see a pattern, but it's not like tremendously precisely estimated. Okay, so that's strategy one. Any questions on that? All right, so that just shows you that there's heterogeneity that appears consistent with liquidity effects. Now, what I wanted to do is find something that approximates the experiment you're interested in, which is directly giving people cash. So it turns out I wasn't able to really come up with a great strategy in the US data. And so what the best I could think of is comparing people who get severance payments, which are lump sum grants when you lose your job. Like if you get laid off from GM and you've worked there for at least 3 years, you might get 2 months of wages as a lump sum when they lay you off. And some other guy might not get that, okay? So the simplest thing you can do is compare the guys who get severance pay with the guys who don't get severance pay. That's a cross-sectional comparison, and no doubt it's problematic because the people who get severance pay are not comparable to the people who don't get severance pay because they tend to have been working for longer, they tend to have better jobs, all the things you might expect. All right, so nevertheless, I think this shows you, what I'm trying to illustrate here is what you can do empirically, sort of given the best you have. I think it's a good illustrative example. So this, taking that into account, let's just compare the effect, the unemployment durations for guys who received severance pay and the guys who didn't. So if you were to interpret this as a causal effect, you would say, yes, the guys who get severance pay do in fact take substantially longer to find a job, and so it does look like there's substantial liquidity effects. Now, obviously the problem is the guys in the red and the blue are not comparable, so what can you do about that? One, you can control for various observable factors, but as I've been stressing throughout this class, in and of itself, that's not a very compelling approach. So, but in any case, that doesn't end up changing things much here. Here's a second test that I think suggests that this might be a causal effect, but I wouldn't completely, hang my hat on this. So what I do is, again, think back to the basic predictions of the model. For people who do not have much money, the severance payment should matter a lot. For people who have $20,000 in the bank, getting a $1,000 severance payment, if this is really a liquidity effect, should basically be irrelevant. So split the sample into those with below median net wealth versus those with above median net wealth. And again, it looks like, as you'd predict, the effects are bigger for those below median net wealth rather than those above median net wealth, which makes you think that maybe this basic pattern here reflects a causal effect rather than just a correlation, because you wouldn't ex ante have formulated an emitted variable story that would have had this differential impact across low and high wealth people, right? So I think that kind of approach can be useful in figuring out if you're identifying causal effects, even though you don't have the perfect quasi-experiment. Questions? Okay, so putting, so this quantifies that with a hazard model. Let's skip that. So putting this together, so what's the idea of the paper? We developed this framework where there's a formula for optimal insurance in terms of liquidity and moral hazard. Try to estimate those parameters in the data, say something about policy. So this is the last part, say something about policy, right? So plug the reduced form estimates of the liquidity effect and the benefit effect into the formula, the decomposition to calculate the welfare gain from changing benefits. And this is the bottom line of the paper. What I find is that the welfare gain from raising the benefit level by 10% in the US relative to the current level, which is roughly a 50% wage replacement rate, is a small, very small, but positive number. And that's important. Positive is important because it says, if anything, the UI benefit level, if you think you have global concavity, which seems to be the case based on the simulations, the UI benefit level is slightly below the optimum, okay, because we're still like on the upward sloping part of the inverted U. How far away are you from the optimum? Where exactly is the optimum? You can't actually directly answer that question. That's the nature of the sufficient statistic approach, that you're only able to estimate local welfare gains. You haven't estimated the primitives of the model. But to get a sense of that, I calibrate the model to match the sufficient statistics. Okay, that's not a rigorous thing because there are various ways in which you can calibrate the model to match the sufficient statistics. There are going to be various calibrations. That's exactly the idea of the whole approach, right? That there's no one model that matches these two parameters. But in models that seem sensible, calibrated to match the statistics, dWdB falls rapidly with B, meaning like that function, W of B, is very curved. And so what that tells you then combined, so that says the second derivative is quite large. And so combined with the fact that this is a pretty small number, sort of the bottom line of the paper is we're somewhere close to the optimal benefit level in the current regime. Yeah. Okay, so so that's the basic logic of this formula in the empirical work. So now I want to address some of the questions that were raised about the quality of the evidence on severance pay. And as in many other contexts, you can do much, much better when you have administrative data, in particular at the time from other countries. So it turned out we started working on the subsequent paper when I gave the earlier paper in a labor lunch at Berkeley, and Andrea Weber, who was visiting Berkeley, said, I said something like, it would be great if you had some sort of discontinuous variation in severance payments where the guys who had more than 3 years of service at GM get the severance payment, but the guys below don't, and they're going to be comparable and so forth. And she said, well, that's exactly how it works in Austria. And she had the data on unemployment benefits in Austria. So this is this is the QJE paper in 2007 that basically estimates the liquidity effects much more credibly, I think. So exactly as I was describing, we use discontinuities in Austria's unemployment benefit system to estimate liquidity effects. The way it works in Austria, roughly speaking, is that a severance payment is made by firms out of their own funds and is legislated by law to have a certain schedule, a certain discontinuous schedule. So the formula for the severance pay amount looks like this, where if you worked for less than 3 years, you get nothing when you're laid off. You do get regular UI benefits, but you get no severance payment. Then if you had between 3 and 5 years of service, you get 2 months of wages as a lump sum, and then there's some other discontinuities, which we actually do not exploit here. So the key thing that we're focusing on is this jump where these guys who happen to work just a day more get an extra sort of $4,000 on average relative to the guys on the left. So I want to go through this paper both to show you the estimates of the liquidity effects, but also as an example of standard practice in RD design papers, all right? So the first thing you want to do in a regression discontinuity analysis is assess the validity of the design. And so what's the key identification assumption? It's that the guys on the right side of this 36-month cutoff have to be comparable to the guys on the left. And what's the most obvious way in which that can be violated? It's if there's selection around the discontinuity. And if you think about the institutional arrangement here, that might actually be plausible because remember I tell you I told you here the severance payment is made by firms out of their own funds, right? So think about as a firm, I might say, well, you know, I don't want to have to pay you $4,000. So let me fire you in, you know, the month before the 36-month cutoff rather than after. And maybe for the workers I really don't want or something, I do that more. That's going to create selection around the discontinuity and is going to invalidate the whole design. Okay, so first of all, you want to understand institutionally whether selection is a serious problem. So we spent some time trying to figure out if firms actually behave in that way, and it turns out there are court cases brought against firms where you can see how you'd be able to detect easily if a firm tends to lay people off right before the cutoff. And so we think just sort of legislatively it's very difficult to do that in Austria without sort of getting caught and disciplined. The other way you want to assess that is just empirically. So the first test, the first plot you always want to do is just a test for a discontinuity in the density. So what's formalized in a paper by Justin McCrary, but the idea is really very simple. Just plot a histogram of the counts, and if you see a spike or any sort of abnormality right around the discontinuity, you know you potentially have a problem because there's some sort of selection. So this thing basically looks pretty smooth around the discontinuity, right? There's a bump at each year, which we think has to do with people tend to get, you know, laid off in whole year increments, but there doesn't seem to be something particularly, you know, dramatically special about the 36-month cutoff. So that's check number one. Question? Okay, so then the second thing you want to do, that's just like selection sort of on counts. So then you want to assess selection on observable covariates to make sure that the underlying assumption here that everything is evolving smoothly except the treatment is in fact satisfied. So in this plot, for example, we show age, the mean age of people being laid off around the discontinuity, and it doesn't look like, you know, you're particularly laying off younger or older workers on one side of the threshold. Now, in general, you'll want to do this for a lot of covariates. So what I find to be a useful technique when you have lots of covariates, and especially when you have a lot of data, is to aggregate those covariates to figure out how much of a selection problem you have. So some of these jumps here, when you have, you know, 1 million points behind this graph, like in this case, any small deviation, even like this, or we see something in wages, small jumps are going to be statistically significant. So often what you'll find in large data sets is everything is statistically significant, right? So that's not a good test of whether you have whether you have a selection problem. I mean, if it were, the way you would solve it is throw out half your data, which obviously is not the way you want to proceed. So, okay, so here's a technique that I think is quite useful. So what we do here is run a hazard model where we're looking at the probability of finding a job, okay? And regress that, or the more general version of this is regress an outcome, the outcome you're interested in at the end of the day. So let's say log unemployment duration on all the covariates you have, all the observable covariates, right? So it would be like B1 age plus B2 prior wage, you know, gender, et cetera, right? Okay, so then you only use the observable predetermined covariates, not the treatment. So then you form a prediction, a predicted duration for each guy, or in this case, a hazard ratio. Same basic concept. So you've got a duration hat of IT for each person. It's like, what is the duration I would predict given the covariates that I see? Or what's the hazard that I would predict given this person's covariates? And then plot the predicted values against the running variable on the x-axis, right? And so the ideal way to do this is you do this graph first with predicted durations, and then you do the graph with actual durations, and you can get a sense of whether the degree of selection is on the same order as your treatment effects. And if you're seeing jumps that look anywhere close to your treatment effects, then you have a serious problem. And if you don't, then you're basically good, right? At least from the perspective of selection on observables. So is that clear? So that's basically what we're doing here. We're plotting mean predicted hazard ratios. So what's the hazard of finding a job for this guy relative to the baseline guy? And you can see it's smooth around the discontinuity. Okay. So you do a bunch of checks for the validity of the design like that, and then you can, it's totally straightforward, you plot the treatment effects, right? So this is showing you mean unemployment durations in Austria. So average number of days you're unemployed, just plotted against job tenure. And you can see that there's a very clear jump on the right relative to the left. The guys who are getting the 2 months of wages, the lump sum grant, are in fact taking significantly longer, about 10 days or 2 weeks longer to find a job. That, I think, is much more compelling evidence that there is, in fact, a causal liquidity effect here. Okay? And then you can quantify its magnitude and so forth, which is what we do here, and I'm not going to go through that. Okay, so any questions on the study?
Can you see if they get like different quality jobs?
I'm going to talk about that next. Yep. Okay, so all right, so that was moral hazard and liquidity. Now I want to talk about the next approach, the third and final approach we'll talk about on optimal insurance. And I should emphasize, these are 3 approaches we've discovered to date. There are surely like other ways of doing this that might have other advantages. So Scheimer and Werning derive a formula that's in terms of reservation wages instead of these other parameters. So in order to talk about that, you need a model where there's a reservation wage choice. That is, people are selecting which job offers to accept rather than a search intensity model. So their baseline model has only a reservation wage choice and not a search intensity choice. But as in all these other papers, they show that their formula still applies if you make a search intensity choice on top because of the usual envelope type of argument. All right, so let's just write down a very simple reservation wage model, and then we can see how we derive their formula. So in this model, the probability of finding a job, which I'm going to call E, is determined by the decision to accept or reject a wage offer, not your search effort. Wage offers are drawn from some distribution. So it's like I get a bunch of jobs, a bunch of different wage offers distributed according to some F, and I take the particular wage that I get and see if I want to accept it. So I'm going to take a case now to make the simple, totally static model. They actually do this in a dynamic model, similar to what I was talking about before, but it's easy to see the idea in a static model. So, so the way this works is you draw a wage offer, and either you reject it or you accept it, and that's the end of the model. So in that static environment, your policy is actually really simple. You reject the offer if your net wage, W minus T, where T is the tax, used to finance the benefit, is less than the outside option. What's the outside option? You can get unemployment benefits of B, right? And so that implies that the probability of finding a job is E, which is 1 minus F of B plus T. It is the probability of getting an offer that pays above B plus T. Okay, so with that decision rule, we can write the agent's expected value prior to job search, before he actually makes this, the draw from the distribution, as follows. It's the probability that he gets an offer that he wants to accept, that's this part here, times his expected utility conditional on getting an offer that pays more than B plus T, right? So that's what this expected utility is. It's utility given this wage draw, but you're only going down that path if W minus T is greater than B. And then if you get a wage offer that's low, you're going to reject it. That happens with probability F of B plus T. And in that case, you get U of B. So that means that your reservation wage prior to job search, so before you actually make this decision, is going to be satisfied by this expression here, where the way to think about this reservation wage is, suppose somebody comes along and says, one of your options is to draw from this distribution, and we know that's going to give you utility of W of B. But I'm going to give you this other option of, I just give you a job with certainty right now. What is the wage rate I'm going to have to offer you in order to make you indifferent between taking my current offer with certainty and going through the stochastic process of drawing offers. That's the way to think about the reservation wage prior to job search, right? And the way you're going to answer that question is say, I'm willing to take a wage of W naught bar such that this condition holds. If W naught bar is above that level, then I'm happy to take that job. I prefer that to searching. And if it's below, then I'd rather search. Okay? So that's the reservation wage. So what is the government trying to do? As usual, it's trying to maximize the agent's utility, expected utility, subject to the government budget constraint. And so then here's basically the core of the inside of the paper. So I'm trying to max W of B, which I know is equivalent to maximizing this because I know this equals that, right? So max W of B is equivalent to max of U W naught bar minus T. This is just a monotonic transformation of W naught bar minus T. So U is just monotonically increasing in consumption, right? So that's equivalent. That problem is isomorphic to maxing W naught bar minus T. And so as a result, I can write dW dB as dW naught bar dB minus dt dB. So these two terms here. And then the whole thing would be multiplied by U prime, but that's not, it's not critical for finding the optimum. And then this term here, as usual, comes from the budget constraint. That's not different across any of these formulas. It's always the same thing. It involves the behavioral response and the level of search effort and so forth. And so what do you get here? A formula for dWdB that depends upon the usual elasticity of search effort with respect to benefits. And now this totally different parameter, dW naught bar dB, the effective changes in benefits on reservation wages. Again, you do not need to know risk aversion. You don't need to know consumption. You also don't need to know the moral hazard liquidity thing. Instead, you just need to know this reservation wage sensitivity to level of benefits. So what is that parameter? That parameter is, if I could run an experiment, I raise benefits by $1, how much do people's stated reservation wages rise? How much more selective do they want to be in choosing jobs? Okay, so they do not do empirical work in this paper. They use estimates, prior estimates of dW naught bar dB, reported by Feldstein and Paterba, where you get data on W naught bar based on survey responses. You ask people what's the minimum wage you'd be willing to accept at a new job, right? To ask a bunch of unemployed people. Okay, so they take the Feldstein-Paterba estimate, plug it into their formula, and they find gains for UI benefits that are quite big, much bigger than my paper, for instance. Now, so there's nothing, I think, problematic with that logic. I think the problem is empirically, these reservation wage elasticity estimates are questionable because they're not actual behavior. They're based on these survey responses. So for example, one thing people often note is that a very large fraction of people, you see them ex post having accepted jobs where the wage rate is below their stated reservation wage from before. So who knows what you're actually getting with the reservation wage, right? There's another issue, though, which I think is quite important and then relates to the question you asked. If you're in a reservation wage model where this margin really is important and you can identify in this way, you should see that when you give people higher benefits, they take longer to find a job, and if they're setting a higher reservation wage, we should see them in a job that's paying more ex post, right? We should see better outcomes ex post. And the fact is, you absolutely do not see that. So there are several studies now using the European admin data sets that show that there is no evidence of match quality impacts of paying higher UI benefits. So let me show you that from the Austrian data. So I showed you this figure, right? This is the severance pay discontinuity. You take longer to find a job on the right. This is a plot of subsequent wages for the same guys. Wages on the job after you found a job, right? On the next job you found. Actually, it's actually the wage growth from the previous job to the next job, just so we can take out heterogeneity in wages across people. It makes it more stable. And you see nothing, right? I mean, if anything, maybe it looks like it's a little bit lower on the right than the left. It doesn't look like it's higher on the right. And I think this is really important, not just from this pure welfare point of view in the context of these models, but from the political debate. Like reporters ask all the time, is an important rationale for providing UI that you can get people to find better jobs and that's going to improve economic outcomes in the long run and growth? The evidence seems totally clear that the answer to that is no. If you favor providing UI benefits, it has to be purely on the basis of short-term consumption smoothing, which I think is valuable, and we try to quantify those benefits. But it's not that somehow you're going to end up improving the economy in the long run. That effect is just not that big. You might also say, well, wages are only one dimension of match quality. What if the jobs are better on some other dimension that you're not able to observe in the data? So that's a perfectly reasonable argument. But a good way to get at that is to look at how long the next job lasts. Okay, so this is an idea that goes back to Jovanovic on match quality. If a match is better on some unobservable dimension, we should see intuitively that match lasting for a longer amount of time, right? If you found a job that you really like that's close to your house or whatever, you would expect that you'd stay at that job for a longer period of time, right? So plot the hazard of exiting the next job, sort of the duration of the next job, around the same discontinuity. And again, it's totally smooth. There's no evidence of increased duration of match ex post relative to, for the guys who get the severance pay versus the guys who don't. Let me show you one other set of graphs and makes an analogous point. So there's another discontinuity in the Austrian system, which is a function of how many months you were employed in the past 5 years, okay? And the guys on the right side of this line get 30 weeks of unemployment benefits, and the guys on the left get 20 weeks. So this is a discontinuity in the duration of unemployment benefits, which we also study in that paper with Card and Weber. Again, you see that the guys who get longer benefits take longer to find a job, so mean duration is higher. But if you look at subsequent wages and you look at subsequent job duration, there's absolutely no evidence of an effect. So that, A, makes me think the match quality benefits are not that important, and B, it's hard to think about how the reservation wage approach would work in light of this evidence. It just doesn't seem like that margin is that elastic.